Last week we have learned the very important unit equilibrium equations, which states that the pressure increase due to the body force. Okay. Sorry, there's something wrong with because something wrong with my PC. I don't know. I sure. Sorry, that's 1 minute. Sure. To share. Okay. Last week, according to Newton's second law, okay, this is from Newton's second law, we draw FBD, and then because it's at the rest, it's in static. So in x direction, y direction, z direction, the components of surface force and body force, the resultant should be equal to 0, right? And so accordingly, we have the formula is called unit equilibrium equations dp dx equal to zo x, dp dy equal to zo y, dp dz equal to zo z. Here, P is actually the pressure, right? X, Y, dx, dy, dz, that means the pressure spatial derivative in X, Y, Z direction. Capital X, capital Y, capital Z is actually the X, Y, Z component of body force, and it's body force per unit mass. And from this formula, it's clear that in static flow, it's because of the body force, the pressure will change. No body force, no pressure difference, okay? And also very important, pressure increase in the direction of body force. So when we introduce the item equipressure service, which on the surface everywhere the pressure should be equal. Equal pressure surface should be perpendicular or should be vertical to body force everywhere. That's why in horizontal, if we only consider the body force, the gravity force, the equipressure surface, or here, the free surface should be horizontal, right? Because for this, the body force is downward, the gravitational force is downward. So the equipressure surface will be always perpendicular to the but the direction of body force is very important, okay? So, and also it's very important that equipressure surface will be always parallel to each other, just like here. It's for sure free surface is a equipressure surface where the pressure equal to the ambient pressure everywhere, and so others the its equipressure surface should be also parallel to the free surface. And we found out the pressure distribution under gravity is equal P. Here we have P equal to P naught. This is the pressure at the free surface plus the pressure due to the fluid weight. It's equal to rho g. This one is actually, we use h. H is actually the vertical depth, is the vertical distance to the free surface. Okay, so we have this important formula, which is the pressure distribution under gravity. This one also tells us the pressure increase due to the gravity force. And this one apply to incompressible flow and incompressible apply to the same fluid. That's I always say same fluid, same level, same depth to the free surface or same depth to the equal pressure surface, same pressure. Okay, here we have this figure. We have said just like A, B, C, D, E, F, G, because the vertical distance to the free surface just all equal to H. So the pressure at these points should be equal to each other and equal to the atmospheric pressure plus rho g. H is actually the depth to the free surface. Okay, this is very important. And also from this figure, we have said it shows that just like PA, PB, PC, PD, and they all perpendicular to the surface. So pressure is always perpendicular to the surface and point to the surface, okay? And pressure is independent of its orientation. So that's why here PA equal to PB equal to PC, okay, equal to PD, okay? And also we introduced the definition of gauge pressure and absolute pressure, okay? Gauge pressure is actually a relative pressure. And then last week, actually, the key point is the how to measure pressure, okay? The barometer and the manometer. Manometer, and we know it's very, very important. I also ask you to do the exercise by yourself. We always need to remind yourself any 2 points at the same elevation in a continuous liquid have the same pressure. This one, any 2 points. I think I need to watch. Okay. Okay. Always need to remind yourself. Always need to keep this in my mind. Any 2 points at the same elevation in a continuous liquid, that's the same fluid, okay, have the same pressure. Just like here, for this, I don't know what's wrong with my thing. Just like this one. Sorry. Okay, just like here for this manometer, and we have two, we only have one fluid and it's continuous, right? Because this is U-tube and continuous. And so any 2 points, just like here, B and C, that they are at the same elevation, okay? Same level, and they will have the same pressure. That's why PB equal to PC. And for A, we can also find A prime, and they will also have the same pressure. And accordingly, PB will equal to PA prime plus the pressure due to the liquid column, okay? And for this example, we have 3 different fluids. So it's very important when you apply the same fluid, you apply the same elevation, the same pressure, need to always keep in mind it only apply to the same fluid. That's here we just like have, we have PC equal to PD, and for PC equal to PD because it's the same fluid. And however, we can't have this. We can have this just like This is A, this is E, F. We can't write PE equal to PF. Why? Because here E, F, they located at different fluid. So should be always be careful. Only in a continuous liquid, only in the same fluid and same elevation, same pressure. And this one you already do the exercise by yourself. Okay, this one, right? So we have other devices, just like to measure pressure drops. Manometers also can be used to measure pressure drops across valves, pipes, heat exchangers. Just like here, we have this tube. We have two sections. We have section 1. We have section 2, and we can use this to find out the pressure drop between between section 1 and section 2. Okay. How do you do this? Can anybody try how to find the pressure at P1 and P2? The section from section 1, section 2, section 1, the pressure is P1, okay? And we can ignore its pressure variation with the pad. That means the pressure is uniform distributed in the section, okay? Or just it doesn't matter, just use this one or just at here at the so I can't just today I'm a little bit confused because I use different computer. Before I use my PC, my laptop. Today I use my PC. So can we say P1 equal to P2? No. Why not? Why not? Because we had two fluids, right? So only we can say here. I don't want to something wrong. Okay, just like here, only we can say this is A, this is B. We can say PA equal to PB, right? Because same elevation, same fluid, or in the continuous fluid. So same pressure, PA equal to PB. And so we can write down PA is equal to P1, PA equal to P1 plus what? PA equal to P1 plus rho G H plus A, right? PA equal to P1 plus, because the pressure PA will equal to P1 plus rho G H plus A, right? Because the pressure at point A or at surface A is actually equal to the pressure P1 plus the weight due to the fluid. And we know that here it's vertical distance to surface one, vertical distance. So here should be rho g h plus a. It's very important. Some students will get lost here. So PA equal to P1 plus rho 1 g h plus a. H plus a is the depth. And how about the PB? PB, here we got two fluids, right? So PB equal to P2 plus rho 1 GA plus rho 2GH. Right? Be careful here. For PB, we have for PA, we have P1 plus lower G, the depth, the vertical depth to service 1. And for PB, for PB, we got 2 fluids. So we need to pay attention when you calculate the pressure at level B. Sorry. When you calculate the PB, you should be careful. We got 2 fluid. We got this part and this section. Okay. And here also you need to know that if it's not liquid, if it's gas, because for the gas we ignore the pressure difference due to the elevation difference. Okay, so if it's gas, we will have P1 equal to PA, P2 equal to here C, well equal to PC. Okay, so if it's liquid, just like here, if it's gas, if it's liquid, if it's water, so when you write down the PA, you need to add the weight due to the liquid. Okay, in this segment. However, if it's gas, if it's air, and so for air, the pressure we just regard the equal in this. Here we ignore the pressure difference due to the elevation difference. So P1 will equal to PA. So here we have P1 equal to PA. I mean, if they are gas, okay, or if they are, just for example, if they are air, this is to find out the pressure drop. Okay. We have here the hydrostatic force distribution plane surface P equal to 0 because we use why we P equal to 0 because we use gauge pressure, right? We use gauge pressure. Gauge pressure is a pressure, absolute pressure minus the ambient pressure. So what's the difference in effective force on the bottom vertical surface and horizontal ones? Can you tell me? What's the difference? For the bottom, it should be uniform distributed, right? Because pressure will equal to dou GH. H is a vertical distance to the free surface. But how about the side? Side surface, it should be triangle, right? This is a pressure difference because we know pressure increase in the direction of the gravity force, just like here. And so according to what we have learned in theoretical mechanics, we can find out the resultant force of these uniformly distributed forces, right? Fr will equal to, Fr will equal to what? Fr will equal to P times the area, right? And also it acting to the Fr, the resultant force we're passing through is centered. Okay. How about this triangle force system? For this triangle force system, we also know how to calculate its resultant force, right? its resultant force is actually equal to the area it covered. So for this triangle force distribution, we know the total pressure or the pressure force P will equal to its P will equal to gamma H. Gamma H is here, right? Times the area. The area is H. The width is D, right? This will be and divided by 2. It's the area covered by the triangle, right? And also the resultant force passing through the center of the triangle. So according to what we have learned in theoretical mechanics, and the pressure force, the triangle pressure force will pass through right, and here will be 1/3 h. This is what we have learned in theoretical mechanics. And draw this diagram of pressure distribution. And this one again, we have this AB and BC. And for B, point B, and we have the pressure perpendicular to surface AB. We have the pressure perpendicular to BC. Right, pressure for static pressure, hydrostatic pressure, they are always perpendicular to the surface and point to the surface, and it is independent of the pressure orientation. Right, and for this one, it's a curve AB, and similarly, the pressure always perpendicular to its surface. So it will be always along its normal line, right? Well, it's a normal direction, right? And it should be intersected at the O, right? In real life, we use hydraulic lift. Just for the car, we always have a hydraulic lift with the car. For the hydraulic lift, how it works. Here we apply a small force. We can get a big force. How? Why we can get a big force? Inside it should be liquid, just like water, like gas. If it's gas, kind of worked. I mean, generally, just like this is water, we can apply a small force. This water, we can apply a small force to get a big force. But if it's air, can we apply a small force to get a big force? No. And first, so how can, if it's water, how this works? Pressure applied to a confined fluid increase pressure through by the same amount. This is because we have said liquid, just like water, is incompressible and air is compressible. For incompressible fluid, any pressure distribution will pass to everywhere the same pressure distribution. So just like here, we have this force F1. We have this force F1, and so we have this pressure increase P1. And so for the increase incompressible fluid, it will pass everywhere to just like everywhere, the pressure will increase with P1. And so service 2, the pressure also increase to P1. That means P1 equal to P2. For incompressible fluid, any pressure distribution will distributed everywhere equally. So we have P1 equal to P2. So accordingly, we have F1 over A1 equal to F2 over A2. So finally, we got F2 equal to F1 A2 over A1. A2 over A1 generally are not are huge. So that's why we use we apply a small force and we'll gain a big force. However, if it's not water, if it's air, the pressure, if we apply this force F1, it will be compressed, right? It will, at the surface 1, it will be compressed, but surface 2, nothing happened, right? So this is Pascal law. We apply to hydrostatic lift, hydraulic lift. Okay, and for diving, we know that if we go to diving, we should be very careful. We should be very careful. We just like here when you dive to that depth 100 feet each, and according to the pressure distribution law at point 2, the gauge pressure, we mean the pressure relative to the ambient pressure will equal to rho g and z or rho g h. Okay, so here we will find out that when you dive down to 100 feet below the free surface, the gauge pressure will almost equal to 3 atmospheric pressure, and the absolute pressure will also reach to 480 atmospheric pressure. And if you need to ascend to the surface, you should need to be very careful. You should be take it slow. Why? Because according to what you have learned in middle school, we have P1, V1 equal to P2, V2, right? Because we have the gas flow, right? So we have P1, V1 equal to P2, V2. And so we will find that when you go up from point 2 to point 1, and the non-volume will increase by a factor of 4, it's very, very dangerous. It will result in embolism or even death. So you should be very careful. Okay, so you should take it slowly to ascend. Actually, there is kind of fish. The fish, if we just got the fish and we need to lift it slowly, or it will explode because it's long volume increased. Okay. And also in some shopping mall, you will see this. Here you see in the middle there is high tank, and this is open. Okay, that means you can push your hand to touch the fish in the tube tank. Why is it possible? It's because it's because the atmospheric pressure, right? As we have discussed before, it's because the atmospheric pressure, because this is negative pressure, because here in the up, it's actually the pressure is lower than the atmospheric pressure, so it can support the water column. Okay. So today we will talk about the relative equilibrium liquid. We just have discussed fluid is at rest, but here just like the liquid is the water is inside this car, and this car is actually moving with acceleration a. So with a constant acceleration, what will happen? We know that if this one is at static, the free surface should be horizontal, right? Because it will the free surface or equilibrium surface perpendicular to the body force. However, if it moves with the uniform acceleration A, according to what we have learned in theoretical mechanics, here, except the gravity force as a body force, we also has the inertial force, right? Recall what you have learned about the inertial force. The inertial force equal to ma, right? The inertial force equal to the mass times the acceleration, and the direction is opposite to the acceleration, right? And here x big capital X is the x is the body force per unit mass. That's why here m is equal to 1. So we have the A, okay. So again, very important here, not only the gravity force G, also here we have the inertial force A. So the body force the resultant body force, here we use parallelogram law, we have the resultant body force. So this will be the resultant body force, and then the free surface should be perpendicular to the body force. So here, instead of to be horizontal, and the free surface should be inclined. Okay, so we can do it step by step. We use the unit equilibrium equation here. And again, this is the unit equilibrium equation. The pressure change in x direction because the body force in x direction. The pressure change in y direction because the body force in y direction. The pressure change in z direction because pressure in because the body force in z direction. Capital X, Y, Z are the body force in X, Y, Z direction. Okay. And in X direction, we have, sorry, in X direction, we have the inertial force. In Y direction, the inertial force equal to 0. In Z direction, we have the gravity force. So we can do the integration and we can find out the pressure distribution. That means if you give the X, give the Z, we can decide the pressure at the here again, we have the constant. How to decide the constant? We know that we can apply the boundary condition to find out the constant. And the free surface here in the coordinate system, if x equal to 0, z equal to z naught, p equal to the pressure at the free surface. So we have, so we can substitute x equal to 0, z equal to z naught, and p equal to p naught. Finally, we can find out constant equal to p naught plus rho g z naught. And this is the pressure distribution we can write down. Okay? So here we need to find out the mathematics expression for the free surface. Then how to find it? we know this is the pressure distribution formula, and we rewrite them. In mathematics, we just rewrite them. Okay, this is the same, exactly the same, right? P equal to P naught plus rho G, and then we just have B naught minus Z and minus this have A over GX. Okay, the pressure on free surface because all equal to the ambient pressure, and then we can find out actually this ds is actually the coordinates of the free surface, but equal to minus the coefficient is equal to minus a over g x plus z naught. Okay, z naught is actually the coordinate system. Here, this is the coordinate system I set up. You can set up another coordinate system by yourself. You will have almost the same expression. Okay, so you see here, this one is exactly the linear equation, right? Ds is a linear function of its x. So you can definitely we know the free surface is actually inclined. It's linear, okay. But Zs is proportional to x. This is equal pressure surface. And according to what we have learned, the equal pressure surface will always parallel to each other, right? So we will know here this is this one is also uh, um, equal pressure surface. So we organize this equation. Sorry for the there's something wrong with the and I don't want to derive this. It's a little bit not difficult. We can do this together if you are interested. But I think it's very important just you know this. So here, from the mathematics, we can find a very interesting conclusion that P equal to the pressure plus rho GH. What does it mean? Here, if you want to know the pressure, and then it will equal to the pressure at the free surface plus the pressure due to the weight, due to the liquid weight, P equal to plus rho GH. That means even you are moving with a constant acceleration, A, the pressure distribution still follow the law of static pressure during the okay. So the distributional law of static pressure during the container, which does horizontal or vertical motion at a uniform acceleration, actually follows the rules of a static fluid. Okay, so this is the free surface, and we can find the slope. Okay, we find the slope is equal to dz of dy is actually equal to a of g. Okay, and we know the equal pressure should be always parallel to each other. So the dashed lines are all parallel to the free surface. And the pressure at any point is only decided by its vertical distance to the free surface. So you can use what you are familiar with the static fluid. P equal to P naught plus gamma H, or equal to P naught plus rho GH. Why? Here, I don't want to do the exact mathematical derivation, but here we can do it by this way. Just like here, we have This is P naught, right? And here, I want to find the P1. And from this one, this formula, actually, you can use this formula to calculate the pressure at any point. For P naught, the ambient pressure, and P1, they have the same X and different Z, right? That means the pressure difference between the free surface and the P1 is only decided by their Z coordinates. They are not, uh, yeah, sure, just for just like this point, if they have different X, they will have the X can affect its pressure values. But if they have the same X, right? If they have the same X coordinates, the pressure, well, they decided by its Z coordinates. Okay, that's why we have the pressure distribution P equal to pressure at the free surface P naught plus rho g h. It's very important. You always need to here h is the vertical distance to the h is a vertical distance to the free surface. Okay. So at the beginning, we said in this chapter we will talk about the pressure distribution for the equilibrium for the fluid at static. The fluid at static, including at static at rest, refer to um, the Earth, refer to there is no relative motion between the fluid and the container, right? Or there is no relative motion between these fluids, okay? So they are still regarded to be at rest. That's called relative equilibrium. Okay. So from here, from this one, if some students are confused, say the body force here, the body force not except the gravity force, we also have the inertial force to be body force. Some students said, I'm confused of this. If you confuse this, you can use Newton's second law, right? You can apply Newton's second law, just still you have this cubic fluid element, and then you draw FBD, and you will have the surface force, right? You will have the surface force. This surface force will be the pressure, right? The pressure force. And you also have the body force, right? Body force. And again, body force, you only have the gravity force. Yeah, it doesn't matter. And then according to Newton's second, you will have the resultant force. Sigma F here is resultant force, well, equal to, for example, in x direction, we'll have a resultant force, well, equal to um, MA, right? Resultant force from the Newton's second law F equal to MA. So this is Rho density. Okay, this will be in x direction only the pressure gradient, right? We have this, and then dp dy equal to 0. So you can apply Newton's second. Also, you can use the inertial force to be also be regarded as body force. Will have the same right. Okay. So anyhow, for this one, you always remind yourself first, when the car moves with a constant acceleration, the free surface will not be horizontal anymore because the body force here is not vertical, but the force will be inclined. And so the free surface perpendicular to the body force will be inclined. Okay, here. This is the first thing. And the second thing you need to know is the slope is decided by the ratio A over G. Okay, A over G, the ratio A over G. And the third thing you need to know is P equal to the free surface pressure plus the weight. Actually, the vertical weight of the fluid column is still follow the law of the static fluid and should be rho g h. H is very important, is the vertical distance to the free surface. Okay, and so we can use this to solve this example. If you just have a cup of coffee and to hold, and if it's at rest, coffee is 7 centimeter deep. And if you then with an acceleration 7 meter per second square, and whether it will spill out or not. And also we need to find out the gauge pressure of point A. How to do this? First, when we start there, the free surface, the dashed line is the horizontal, right? It's 7 centimeter. And if you move with an acceleration, and the free surface will be inclined, right? It will not remain horizontal because you have the acceleration A, right? And so this will be total. This will be the resultant body force, right? And body force perpendicular to the free surface. We can find out. We can find out this theta. This theta is how to find out this theta. This theta is equal to this one, right? This perpendicular, the body force perpendicular to the free surface, and the gravity force perpendicular to the horizontal. So this is equal to theta. So we will have tangent theta equal to AXG. And tangent theta also equal to delta Z over half D, right? This is half D, right? And so we will have this delta Z. That means when you move with a constant acceleration, the increased height of the coffee delta Z will equal to the radius of the cup times tangent theta, where theta is actually decided by the ratio of the ratio of the acceleration you are moving per the gravity. Okay, so delta Z equal to 2.1 centimeter. So we know that in total it will be 7 plus 2.1. It will not spill out. Okay. How to find the gauge pressure at A? The gauge pressure at A, when just now we said we can calculate the pressure at A. It will equal to the free surface, the pressure at the free surface that will be P naught. And because we find the gauge pressure, the P naught or minus P naught, so we only need to consider pressure force due to the fluid column. So PA will equal to rho G H. H should be the vertical distance to the free surface. The P2 plus what? So this is the pressure at the at point A. How about the pressure at point B? How to find out pressure at point B? The pressure at the point B, again, you can apply the distribution law, right? PB equal to the pressure at the free surface, we mean the absolute pressure, minus, plus the pressure due to the vertical liquid column, right? So PB will equal to rho G HB. HB is actually equal to 7 minus 2.1 centimeter. And then because it's centimeter, okay. So the bottom, for the bottom, this time the bottom will not be equally distributed. Instead, it should be like this, right? This is the pressure distribution on the bottom. Okay. So maybe we have 10 minutes break and then continue.